In episode 92, titled Logistic Regression, Probabilities, Log Odds, and Threshold Strategy, we focus on a classifier that remains a workhorse in real systems because it produces something teams can actually use, a risk score that behaves like a probability. Logistic regression often gets introduced as the classification version of linear regression, but that framing hides the most operationally important feature, which is how it supports decision-making under uncertainty. In many cybersecurity and business contexts, you do not simply want a yes or no label. You want a measure of risk that can be tuned to match workload and cost constraints. Logistic regression gives you that risk signal in a way that is relatively interpretable, stable, and efficient, especially when data is limited or governance requirements are strict. The central idea of this episode is that the model outputs risk, and you choose how that risk becomes action through thresholds. When you understand that separation, you stop treating the model as a verdict and start treating it as a policy tool. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Logistic regression is a method for classification that models the probability of the positive class given a set of input features. Instead of predicting a continuous target directly, it predicts a value between 0 and 1 that represents how likely the observation is to belong to the positive class. The model does this by taking a linear combination of features and then passing that score through a logistic function so the output stays within the probability range. This is why logistic regression can still use many of the same feature engineering and regularization ideas you saw in linear models while producing outputs that have a clearer decision interpretation. The model is trained to make the predicted probabilities align with observed outcomes as well as possible under its assumptions. In practice, that makes logistic regression a natural choice when you need a risk score that can be ranked, thresholded, and communicated consistently. The concept of log odds is the bridge between a linear model and a probability output, and it is worth understanding because it explains both the math and the interpretation. Odds are the ratio of the probability of an event occurring to the probability of it not occurring, which captures relative likelihood rather than absolute probability. Log odds are simply the logarithm of that odds ratio, and logistic regression models log odds as a linear function of the features. This means the linear part of the model operates in log odds space, where it can take any real value, and then the logistic function converts that back into a probability. The log odds view is powerful because it turns multiplicative changes in odds into additive changes in log odds, which fits naturally with linear modeling. Once you see logistic regression as linear in log odds rather than linear in probability, the behavior becomes easier to reason about. Interpreting coefficients in logistic regression follows directly from the log odds framing, because each coefficient represents the change in log odds associated with a 1-unit increase in the corresponding feature, holding other features constant. A positive coefficient increases log odds, which increases the predicted probability, while a negative coefficient decreases log odds, lowering predicted probability. The phrase holding other features constant matters because, as with other regression models, correlated features can complicate interpretation even when the model remains useful for prediction. Coefficients are not probabilities themselves, and they are not percentage changes in risk unless you apply additional transformations and context. What they provide is directional and relative influence on the log odds scale, which can be translated into odds ratios if needed for communication. For many professional audiences,
The safest interpretation is that the coefficient tells you whether a feature pushes risk up or down and by how strongly on the model's internal scale.
The most operationally important step is converting probabilities into decisions using thresholds that match costs, because a probability by itself does not tell you what action to take. A threshold is simply a cutoff value such that if predicted probability exceeds the threshold, you classify the case as positive or trigger an intervention. The default threshold of 1/2 is rarely appropriate in real settings because costs are rarely symmetric, and class imbalance often makes the base rate far from 1/2. If false positives are expensive, such as when each alert requires significant analyst time, you may choose a higher threshold to reduce alert volume and improve precision. If false negatives are unacceptable, such as in safety-critical detection where missing an event is catastrophic, you may choose a lower threshold to increase recall. Threshold choice is therefore a policy decision that ties the model's risk score to business capacity and risk tolerance rather than to a generic convention.
Regularization is often essential in logistic regression when you have many features, especially when some are correlated, sparse, or only weakly informative. Without regularization, the model can overfit by assigning large coefficients to features that happen to correlate with the outcome in the training sample, creating unstable probabilities and poor generalization. Regularization adds a penalty that discourages overly large coefficients, effectively shrinking the model towards simpler explanations that generalize better. This is especially important in high-dimensional settings like text features, telemetry features, or one-hot encoded categories where the number of predictors can be large. Regularization also improves numerical stability, which can otherwise become an issue when features are highly correlated or when the data is separable. The key exam takeaway is that regularization is not only for fancy models, it is a practical control knob for logistic regression in real feature spaces.
Threshold strategy becomes clearer when you practice with contrasting scenarios, because different domains impose different constraints. In fraud alerting, the positive class is often rare, and the cost of investigation is significant, so you may prefer a higher threshold to keep precision high and alert volume manageable, even if recall is somewhat reduced. In churn outreach, the intervention might be a marketing message or a retention offer, and the costs and harms of contacting the wrong customers differ, so you may accept a lower threshold if outreach is cheap or if the opportunity cost of missing churn is high. The same logistic model could be used in both contexts, but the threshold policy would differ because the action tied to the prediction differs. This reinforces that the model produces risk, while the threshold encodes the decision rule that converts risk into action. The correct threshold is the one that best balances cost, capacity, and business objectives, not the one that yields the highest headline metric. It is also important to avoid assuming that the probability output is calibrated without checking, because logistic regression can produce probabilities that are poorly aligned with true event rates under certain conditions. Calibration refers to whether predicted probabilities match observed frequencies, meaning that cases scored at 0.7 occur about 70% of the time. A model can rank cases correctly, separating high risk from low risk, while still producing probabilities that are systematically too high or too low. This can happen due to class imbalance, drift, regularization choices, sampling strategies, or the fact that the model's functional form is only an approximation of reality. If you use probabilities directly to make risk-based decisions, miscalibration can lead to unexpected alert volume and inconsistent policy outcomes. Checking calibration is therefore part of treating logistic regression outputs as risk scores rather than as abstract numbers. Class imbalance has a particular effect in logistic regression because it influences the intercept and the baseline probabilities the model learns. When positives are rare, the model's intercept will typically push baseline probabilities downward to reflect that rarity, and the model will require stronger feature evidence to produce high probabilities. If you train on data with altered class balance, such as through oversampling, the learned intercept can shift in a way that makes raw probabilities misleading for real-world prevalence. This is one reason probability interpretation must be tied to the training distribution and why you should be cautious when resampling. Even without resampling, class imbalance means that a probability of 0.2 might be extremely high risk relative to a base rate of 1%, even though it looks low in absolute terms. Understanding the base rate context prevents you from misreading probabilities and making poor threshold choices. When positives are rare, evaluation should focus on precision, recall, and precision recall curves because these metrics reflect the trade-offs that matter under imbalance. Accuracy can look impressive while the model fails to detect positives, and receiver operating characteristic curves can be less informative about operational workload because they do not directly show how precision collapses as you chase recall. Precision recall curves help you visualize how many false positives you must accept to achieve a given recall level, which connects directly to capacity planning and alert fatigue. This evaluation style also supports threshold selection because each point on the curve corresponds to a threshold and a resulting trade-off. In other words, metrics are not just for reporting, they are tools for designing the decision rule you will use in practice. Logistic regression becomes most valuable when evaluation is aligned with the operational meaning of its outputs. Communicating logistic regression results should emphasize that the model is producing a risk score, not a deterministic label, because that framing aligns expectations with how the system actually works. A risk score supports prioritization, triage, and policy setting, allowing teams to decide which cases deserve attention first. It also supports transparency because you can explain that a higher score indicates higher estimated likelihood, while still acknowledging uncertainty and the possibility of false positives and false negatives. Treating outputs as deterministic labels invites people to demand certainty that the model cannot provide and to overreact to inevitable mistakes. Communicating risk also makes threshold policies easier to explain because you can describe them as choosing how much risk is worth acting on given limited resources. This is a more honest and more operationally useful way to present classification outputs. Monitoring drift is essential because the mapping from features to probabilities can degrade as the environment changes, even if the model structure stays the same. Drift can shift feature distributions or the relationship between features and the target, causing predicted probabilities to become miscalibrated or less discriminative over time. In operational settings, you might observe that the same threshold that produced a manageable number of alerts last quarter now produces a flood, or that recall has dropped even though input distributions look stable. These changes indicate that the risk score is aging and that retraining, recalibration, or threshold adjustment may be needed. Because logistic regression outputs are often used as a calibrated signal, drift can be especially damaging when it goes unnoticed. Monitoring should therefore include performance metrics, calibration checks, and changes in the score distribution to detect early warning signs. The anchor memory for episode 92 is that logistic regression outputs risk, thresholds turn risk into action. The model's job is to estimate relative likelihood, producing probabilities that support ranking and decision design. The threshold is the policy choice that decides how much risk justifies a response, given the costs of false alarms and misses and the capacity of the organization. Keeping these roles separate prevents a common mistake, which is blaming the model for a threshold decision or treating the default threshold as if it were part of the model's intelligence. It also reinforces that the same model can support multiple actions with different thresholds depending on context. When you remember this anchor, you approach logistic regression as a decision support tool rather than as an automatic judge. To conclude episode 92, titled Logistic Regression, Probabilities, Log Odds, and Threshold Strategy, choose one threshold decision and explain why it fits the situation. For a fraud alerting system with a small investigation team, a higher threshold is often appropriate because each alert consumes human time, and false positives create real cost and fatigue, so you prioritize precision and keep volume within capacity. The trade-off is lower recall, meaning some fraud will be missed, but that trade-off can be justified when the organization cannot investigate everything and needs a reliable queue of high-risk cases. For churn outreach, where contacting customers may be relatively inexpensive and missing likely churners may be costly, a lower threshold can be justified to capture more at-risk customers, accepting more false positives as an acceptable cost of broader coverage. In both cases, the threshold is chosen to match action costs and capacity, not to satisfy a default convention. Stating the threshold choice in that cost and capacity language demonstrates you understand how logistic regression turns probabilities into operational decisions. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.